You can tell a chemical reaction has taken place if one or more of the following things happen. There's a colour change, there's a temperature change, or a gas is given off, indicated by bubbling, fizzing or a flame. Something new is always formed as a result of a chemical reaction. We'll look at several different types of chemical reactions. Combustion, redox reactions, that's reduction and oxidation, decomposition, displacement and neutralisation. First, combustion, commonly known as burning. When natural methane gas is burned in a furnace, how do we know that a chemical reaction is taking place? What ingredients are needed for combustion to take place? What is the chemical equation for the burning process? This next clip will help you.
The flame is basically a chemical reaction between the air and the gas. It produces lots of heat and light and also waste gases.
To understand what's really going on in here, you need to get right inside the flame. Fire is a chemical reaction. The flame you see is what comes out of this chemical reaction. Gas is so hot that they're glowing. The chemical reaction happened between fuel, natural gas, and oxygen from the air. But to get the reaction going, it also took heat energy. These are the three things you need for fire: a fuel, oxygen, and heat energy. The chemical reaction produces more heat, energy which is useful, but useful not just to us, it also keeps this reaction going, so long as the fuel and oxygen keep on coming.
One of the jobs I have to do whilst I'm on shift is to take measurements inside the furnace. This involves removing a block from the side of the furnace and poking a probe in there. The probe sucks the sample from the furnace, sends it down a tube to an analyzer, which will tell us exactly what goes on inside the whole furnace chamber. We're trying to reduce the amount of pollution to the environment and also to increase the amount of heat energy that we produce and make the most of this energy.
Let's go through the questions one by one. How do we know that a chemical reaction is taking place? A chemical reaction is taking place because something new is formed, another gas which goes up the chimney, and there's a large temperature change as heat is produced. Next question. What ingredients are needed for combustion to take place? The three ingredients that are essential to produce a fire are fuel, in this case methane gas, oxygen, and heat energy. If any one of these is missing, then the fire goes out. Changing the amounts of any of them changes the rate of combustion. And finally, what is the chemical equation for the burning process? The word equation for the burning of natural methane gas is methane plus oxygen produces carbon dioxide gas plus water. The chemical equation for that is CH4 plus 2O2 gives CO2 plus 2H2O. This burning reaction gives out a lot of heat. It's an exothermic reaction. Here's some more about the fire triangle, filmed after the Gulf War in the burning oil wells of Kuwait.
All fires can be extinguished by applying some simple scientific ideas.
You have three things. You have the heat, you have the source, and you have the oxygen. You eliminate one of those three and you can put a fire out.
Scientifically, it's very easy. Take away any one of these three ingredients and the fire goes out. But in practice, how do you stop the fuel from gushing out of a blown-up oil well? The obvious way is to block it off. These trucks are carrying a type of chemical mud which has to be pumped down the well.
Here we have some of the stingers that are used. The stinging method involves poking one of these mandrels down into the well so that you can pump mud into the well. The mud will overcome the pressure of the well, and when you get enough mud in the well, then the well is dead. This goes on to an end of a boom called an Athey wagon boom. And it's a long extension that will carry the pipe that carries the mud down to the stinger that goes into the well. So the Athey wagon has got a lot of weight. The end of this wagon has got enough weight to hold down the stinger, make sure that it stays in place once it enters the well.
With the well blocked, the fuel side of the fire triangle has been broken and the fire extinguished. But some fires can't be blocked off in this way, so what are the other options? The heat from the fire can be removed, breaking the fire triangle in a different place, and that's often done with water.
We're going to be using the water first of all, and that'll just essentially cool the oil. At the combustion point, you can just see a small area where the oil is leaving the wellbore, and there's a couple of feet there before it starts to burn. Now at that area where it starts to burn, the combustion area, if we start at that point with our water, it will cool the oil and we should be able to chase it right up, thus extinguishing the fire.
The third way of breaking the fire triangle is to remove the oxygen from the fire. Explosives use up all the oxygen around the fire, and that does the job. Alternatively, a dry powder can be used to smother the flames.
And we'll bring the dry chemical in with the cat, and which we'll set approximately about 8 feet away from the well, and the dry chemical will extinguish onto the fire. Which the dry chemical will do is take away the oxygen and snuff it out. It will just automatically put her out, hopefully.
In this case, they're using dry powder and water, tackling the fire triangle from two sides.
The next type of chemical reactions are called redox reactions. That's reduction and oxidation. These next clips start by showing some oxidation taking place, and then go on to explain oxidation and reduction in two different ways.
The shiny surface of aluminium isn't quite what it seems. It's not pure metal. The outermost surface is actually a coat of aluminium oxide. It's a layer just a few atoms thick, so thin that you can see the shiny metal underneath. Whenever a bit of the oxide layer gets scratched off, it reforms very quickly, and that stops the aluminium reacting further. This is why aluminium foil is so good for wrapping food. The oxide layer stops the aluminium reacting with the chemicals in the food. But take the oxide layer away with a kind of chemical polish like this, and kitchen foil comes to life. This is what happens when naked aluminium meets oxygen in the air. The reaction makes so much heat that steam forms near the surface. Still, shiny aluminium is secretly rather reactive once its oxide layer has gone. And if you grind it up very finely, it will even burn. It almost explodes. Heat from the Bunsen burner makes the aluminium react with oxygen in the air, and a spectacular chain reaction begins. The white smoke that's left behind is aluminium oxide.
All burning reactions are examples of oxidation, because the substance that's burnt is oxidized. burning substances are chemically combining with oxygen. The oxygen is an oxidizing agent. But the oxidizing agent doesn't always have to be oxygen gas. Potassium chlorate is a strong oxidizing agent. It's got lots of oxygen in it. You'll see the point of the coin later. The white substance is the potassium chlorate. Phosphorus dissolved in a liquid is added. When it's touched with a hot metal rod, during the flash, the phosphorus was oxidized by the potassium chlorate. The reaction was so ferocious, it was as if the metal plate had been hit by a sledgehammer. Reactive metals like magnesium can even burn in carbon dioxide, a gas which normally puts out fires. The magnesium combines with oxygen in carbon dioxide, coating the jar with magnesium oxide powder. The black specks at the bottom are carbon.
Combustion is one form of oxidation. Rusting is another form of oxidation.
This is wire wool. It's made of iron. The water in this jar has been boiled, so it shouldn't contain much oxygen. But the water in this one is straight out of the tap. An hour later, the iron in the jar with the boiled water hasn't changed. But the rusty red of iron oxide is clear in this jar. Dissolved oxygen has combined with the iron, so we say it's been oxidized. That's true, but it's only one way of looking at it. Look much closer, and you realize that oxidation doesn't center on the oxygen at all. Oxidation is really all about the movement of electrons. This represents the surface of a piece of iron. The iron atoms are organized in a regular pattern called a lattice. Between the atoms, a sea of negatively charged electrons flows freely. When the iron meets water containing oxygen, the conditions are ripe for rusting to take place, because the water and the oxygen together attack the iron. Electrons leave the iron and move towards the oxygen, leaving the iron positively charged. With the help of the water, the oxygen molecules split up and absorb the negative electrons from the iron. They become negatively charged themselves. Remember, the iron is positive, so the opposite charges are attracted to each other and combine to form rust. The iron has combined with oxygen, but it's lost electrons. Here's one way to remember that. Oxidation is loss of electrons. Reduction is the exact opposite. The black powder is carbon, and the light-coloured powder is lead oxide. The lead is locked into the lead oxide, and heat alone won't split them apart. But add carbon, and that changes everything. As the mixture gets hot, 2 lead oxide particles react with 1 carbon atom. Oxygen leaves the lead oxide and transfers to the carbon. That makes carbon dioxide gas. It's invisible and just escapes into the air. But these tiny drops of lead get left behind. They've lost the oxygen they were paired with. So one way of understanding reduction is to say that it's loss of oxygen. But there's another way of looking at reduction, as a movement of electrons. The reason that lead and oxygen stick together in lead oxide is because they have opposite electric charges. The lead ions are positively charged and the oxygen ions are negative. Lead oxide is an ionic compound. But carbon doesn't like to form ionic bonds. Carbon and oxygen will only join together to make carbon dioxide with covalent bonds. So before the oxygen can join with the carbon, it has to get rid of its extra negative charge. The oxygen must give electrons to the lead. The lead ions gain electrons. That neutralizes their charge and turns them into lead atoms. It turns out that whenever something gets reduced, it gains electrons. So chemists actually define reduction that way. They say, if oxidation is loss, reduction is gain of electrons.
So oxidation is gaining oxygen or losing electrons. Reduction is the opposite, losing oxygen or gaining electrons. Remember oil rig. Oxidation is loss, reduction is gain of electrons. These are called redox reactions because they're a combination of reduction and oxidation. When lead oxide is reduced by carbon, it gives lead and carbon dioxide. The lead oxide is reduced to metallic lead, while the carbon is oxidized to carbon dioxide. The next chemical reaction to look at is decomposition. Decomposition is where a substance decomposes or breaks down. There are 3 types of decomposition. In thermal decomposition, a substance is broken down by heat. In electrolytic decomposition, a substance is broken down by an electric current. In catalytic decomposition, a substance is broken down by a catalyst. Both thermal and electrolytic decomposition are used to extract aluminium from aluminium oxide.
First, the electric current heats the aluminium oxide. Heating breaks the strong bonds between aluminium and oxygen. That leaves positive aluminium ions and negative oxygen ions floating in the mix. Next, electric charge draws the ions apart and neutralizes them, turning them into aluminium metal and oxygen gas.
So the heating process first decomposes aluminium oxide into aluminium and oxide ions. Then the electrolysis separates the ions and turns them into atoms of aluminium metal and oxygen gas. The presence of a catalyst can trigger a decomposition reaction. Decomposition using a catalyst can remove nitrous oxide gas from car exhaust emissions. In the presence of a catalyst, nitrous oxide decomposes into safe nitrogen and oxygen gases. Next, displacement reactions. In a displacement reaction, part of a compound is displaced during a chemical reaction. For example, a more reactive metal will displace a less reactive metal from its compounds. For example, copper oxide plus iron gives iron oxide plus copper. The iron displaces the copper from the copper oxide and takes the oxide over for itself. That's because iron is more reactive than copper. Iron oxide plus copper produces no reaction because the copper is less reactive than the iron. But how do you know which metal will displace another? It all depends on their position in the periodic table and where they are in the reactivity series. Potassium, sodium, calcium and magnesium burn easily in air and react with water with decreasing reactivity. Aluminium, zinc, iron, lead, copper and mercury oxidize in air, while silver and gold do not react with oxygen, water or dilute acids. It's useful to know the order of the metals in the reactivity series to help you answer questions about displacement reactions. You can probably think of some memorable sentences made from their chemical symbols, like kings naturally catch magnolias, and so on. Neutralization is another kind of chemical reaction you need to know about. Neutralization is the reaction between acids and alkalis. Let's remind ourselves what we mean by acid and alkali and how it's measured.
If I put universal indicator in orange juice, it turns slightly red. But if I put it into lemon juice, it turns very red. And this means that lemon juice is more acidic than orange juice. Now, if I try these experiments on lots of different substances, I end up with all these colours, from the very red at one end to the very blue at the other end.
If we number them from 1 for a strong acid to 14 for a strong alkali,
With 7 in the middle, meaning neutral, neither acid or alkali, then we have a scale, known as the pH scale. And the pH scale is how acidity and alkalinity are measured in scientific terms.
So the pH is a measure of whether a solution is acid, alkali or neutral. The pH scale goes from 1 to 14, from acid to alkaline. On the pH scale, 7 is neutral. All substances less than pH 7 are acid. All substances greater than pH 7 are alkaline.
If an acid reacts with an alkali, a number of things can happen depending on the two you're mixing together. And one useful one is when you mix the right amount of acid, this one has a pH of 4, with the right amount of alkali, this has a pH of 11. The acid and the alkali neutralize each other.
An alkali neutralizes an acid to produce a salt. An alkali is a soluble base. Examples of bases are metal oxides such as copper oxide, metal hydroxides such as sodium hydroxide, and metal carbonates such as calcium carbonate. Metal oxides neutralize acids to give a salt and water. For example, copper oxide plus sulfuric acid gives copper sulfate plus water. CuO plus H2SO4 gives CuSO4 plus H2O. That's base plus acid gives salt plus water. Combined in the correct proportions, the pH of the acid and alkali cancel each other out, and the pH of the resulting salt is neutral. That's why it's called a neutralization reaction. Two of the most common alkalis are sodium hydroxide and potassium hydroxide. They also react with acid to give a salt and water. Sodium hydroxide and hydrochloric acid give sodium chloride and water. NaOH plus HCl gives NaCl plus 2H2O. That's base plus acid gives salt plus water. Potassium hydroxide and nitric acid gives potassium nitrate plus water. KOH plus HNO3 gives KNO3 plus 2H2O. That's base plus acid gives salt plus water. Metal carbonates neutralize acids to give salt plus water plus carbon dioxide. For example, calcium carbonate and hydrochloric acid gives calcium chloride plus water plus carbon dioxide. CaCO3 plus 2HCl gives CaCl2 plus H2O plus CO2. That's base plus acid gives salt plus water plus carbon dioxide. Notice how neutralizing hydrochloric acid produces chlorides, neutralizing sulfuric acid produces sulfates, neutralizing nitric acid produces nitrates. There's more about chemical reactions in the higher tier science programme. That's it for chemical reactions.